Hi, this is Professor Ray Chen from UT Austin. I would like to use the next 30 minutes or so to give a program review of dynamic photonic tensor cores for a scalable and energy efficient optical neural network. This program is supported by FOSR. This is the outline of the presentation. We'll give you the background and then the hardware efficient design, and then we give you the universal photonic accelerator based on the multi-operand MZI, which is try to minimize the active devices to enhance the size of the matrix. Dynamically operated the photonic tensor core for attention in transformer model. Finally, we'll give you a future plan about this program, and then we'll give you a summary. As you know, we scale the semiconductor technology down to deep nanometer level. Electronic devices are running into fundamental physical limits. On one hand, the higher clock frequencies in the gigahertz range lead to excessive power consumption and severe heat dissipation issues. On the other hand, at the same such a small dimensions, quantum effects start to dominate. Traditional digital processors, including CPU, GPU, and TPU, are hitting an efficiency wall. So to address this challenge, in this program, both academia and industry are exploring new paradigms through which we can really solve this problem. At this point, the industry approach using electronics, their efficiency is still quite low, and also the problem with integrated photonics is a good candidate for next generation to overcome the bottleneck. However, we still have several potential bottlenecks we try to solve in this program. Compared with electronic and photonic computing, the electronics ICs suffered a RC delayed, especially with multi-fan-out structures by light, and waveguides do not have the RC penalty. And the latency is set by the path lengths. In other words, it has nothing to do with the loading. So the optical computing can be 1 to 2 order of magnitude faster when compared to the state-of-the-art electronic computing. Secondly, the metal transmission line have several issues such as skin effect, which make the higher clock rates and high frequencies become very high lossy, which really has created not heat dissipation problem, also energy consumption problems, also packaging problems. So we have the unique multiplexing technology in our case, using WDM to pack many channels into a single waveguide for high bandwidth and parallelism. Also, the power consumption of transistor-based ICs have a cubic relation with the clock frequencies, and also photonic electronic platforms have reached a sub-picojoule per bit efficiency, and therefore the scale linear with the frequency and also the near zero static power. This is another important motivation in the machine learning with the deep neural network is changing the various aspects of our life with applications from image recognition, language processing, autonomous driving, and healthcare. A striking example is the large language model such as GPT. Have billions of parameters training. Like GPT-3 used thousands of GPU for weeks, or over thousands of megawatt hour of energy. So the plot showing here is on the left shows why the previous trend is unsustainable and the demand double about every 3.5 months, which is about 5 times faster than the Moore's law. Okay. So even with the specialized hardware GPU and TPU, the gap will be larger This divergence tells us we need more specialized and far more efficient hardware, which is the motivation of exploring new computing paradigm such as the optical computing we proposed and developed here. A primary challenge in current photonic integrated circuit arises from the micron to millimeter scale size on-chip photonic devices, which leads to a unavoidable trade-off between the PIC scaling to the chip footprint. In other words, the packing density is much lower compared to transistor packing density at this point. And the peripheral electrical components of the EO modulator data access and conversion between the analog and digital domains boosts energy consumptions, thus undermine the power efficiency benefits of optical computing. So to solve these problems, some strategy have been proposed in our efforts. Our previous MURI project, we introduced optical subspace neural network to improve the hardware efficiency by structured compression approach. And on the device level, instead of using multiple optical devices to build a circuit, some use single passive devices such as star couplers or metamaterials to build the optical neurons, which are more compact, but the reconfigurability of this structure is an issue of concerns when the intrinsic fabrication deviation from the original design. So how to improve it? So the idea we propose and then try to demonstrate is to develop a novel multi-operand optical neuron using a multi-operand MZI. By the way, we are the first group propose and demonstrate this idea that features a compact footprint. Unlike the conventional MZI, as you know, it can be as large as many millimeters. So our design incorporates K-active actuators, each controlled by independent electrical signal. This configuration squeezes a length K tensor operation into a single device, achieving a K-fold saving in areas, which is very significant in the context of optical computing when you compare with electronics. So we place a differential multi-operand MZI pair. In each multi-operand MZI, one arm is applied by the WI plus XI. XI is the signal, WI is the weight, or you can also use the WI minus XI, okay, WI minus XI, where the other arm provides a bias that sets state at the more linear region of its transfer function. As you know, because it's analog computing in this case, so the linearity of the transfer curve is important. And also, how can you avoid the high order nonlinear terms? Okay, so by doing so, we can really improve the efficiency of the system. So the idea here is if we measure the positive and negative outputs and subtract the two photocurrents at the output, the squared terms can be canceled out in this case, okay? And therefore, what's left exactly the inner product is a W times X. In other words, the nonlinear term due to the positive and negative signs will automatically canceled, okay? So a nice bonus is that this design can encode two full-range operands on a single actuator. Instead of separate modulators for XI and WI, like in conventional design, such as MZI, the mesh, and the weight bank. And because we can share drive signals heavily, both across in differential pairs and the weight sharing within a unit. In other words, you don't need to have a separate weight matrix calculation. In other words, it can be done simultaneously. the photonic integrated circuit layout becomes much more compact, and the electrical routing is much easier also. So this is the hardware we demonstrated. We tape out a photonic electronic neural chip with the thermo-optical multi-operand MZI with the 4 phase shifters. Here is a micrograph of the customized multi-operand MZI differential pair. In the experiment, we use an FPGA to control the DAC, digital to analog converters, and then encode both the weights and the input, and build the dedicated PC board for signal driving and the readout, as shown in the picture here. So this slide shows you how to calibrate the multi-operand MZI for linear operations. We use a simple 2-step procedures. Okay, step 1 is a transmission calibration for both arms. We sweep the bias and then measure the normalized transmission, fit it with the physical model of MZI, and then get the electro-optic tuning efficiency of each phase shifter. The example on the top right shows the fitting result of the biased arm. Okay, and the step 2 is to find the usable linear region. Since MZI transmission is inherently nonlinear, it's a sine square, as you know. We don't use the full range. Instead, we identify the most linear region. We set a maximum error threshold of 1.5. That's where we carve out the linear regions. Okay, with given the modulation range around 1.52 radians. So this is one of the data sets we calculated. This is a ground truth image. Also, we should note that the core computations of modern deep neural network can be written as one or more matrix vector multiplications after a corresponding reformulation. And the convolution is a classic example. Here we use a standard IM2-core trick. For example, we slide a 3 by 3 window over the image, flatten each patch, okay, into a 9-element vector, and stack those patches into a matrix. Okay, and each 3 by 3 kernel is also flattened into a 9-element weight vector. Then the convolution is just a matrix multiplications between the kernel weights and the patch matrix. With that setup, we run an on-chip image processing demo. We applied here the matrix multiplication here. We have 5 different 3 by 3 kernels to an UT image here. Okay, and the matrix multiplication between the kernel and weight is shown here. Okay, with this setup, we run an on-chip image processing. As you can see, the correct answer can be retrieved quite well with high accuracy, and those filtered image with low deviation from the ground truth, as you can tell from this calculations. So to evaluate how well this design generalized across different artificial intelligence architectures, we run several experiments with different data sets, starting from the basic fully connected layers and the convolution layers, okay, as shown in this chart. We evaluate 2 benchmark, fashion MNIST and also German traffic sign data sets. the German traffic data sets with 43 categories, and the model is a lightweight concurrent neural network where the core convolution and the linear layers are implemented with our chip. So everything else, like normalization, activation, pooling, stay in the standard digital pipeline. And the network size for the MNIST is about 151 kilo parameters, and the German traffic signal data sets is 630 data sets, kilo parameters for the okay. To make this realistic for hardware, we use a hardware-aware training, including the quantization and the noise injection. So the model learned to tolerate limited control precisions in the device noise. Here we use design a 5-bit control for the operands, encoding for weights and input. In terms of the accuracy, we get from this table, you can tell the accuracy we got about 91% for the fashion MNIST and 94.5% for the German traffic sign. The confusion matrix shown here, okay, and the per class plot showing strong performance across the most classes, which tells us the optical layer are working well in a practical version workload. Here is another data set from the NIH brain MRI image. The more challenging task is this is medical image segmentations using the brain tumor segmentation data sets. Okay, the input is a 4-channel MRI slice, including the flare T1, T1s, and the T2. And the goal is to predict a pixel-wise mask with the 4 classes. Okay, we use a 2D UNet, and we take the ResNet 50 as a encoder backbone. Consider the network size is quite large. We just replace the convolution layers in the encoder with our multi-operand MZI-based optical convolution wrappers. Using this setup, there are 11 million parameters, roughly 15% of the total. Again, we use a hardware pipeline. Here, we report a DICE score, which measures the overlap between the prediction and the ground truth. And on the test set of 70 patients, we achieve an average DICE of about 0.75. At the bottom, we can also show an example here across the 4 MRI sequences, plus the overlay of the ground truth and our prediction. The predicted tumor regions closely match with the ground truth, okay, including edema and enhancing the tumor, and also the core region, which shows the approach can extend beyond classification of dense pixel level version tasks. So this is the slice image we took. Okay, now we can push the same hardware idea beyond the vision into language model. We train the autoregressive transformer on the Wikitext 2 and the Wikitext 103. Okay, for a next token prediction task. The key differences is that we map the self-attention computation onto our optical engine. So query, key, and the value matrix are still produced by digital layers, but the heavy matrix multiplications inside attention are handled by the optical blocks, as shown here. Okay, this language model has about 25.7 parameters in total. So it's not in the large language model. It's pretty much you can define the small language model due to the matrix size. but it is showing the advantage using optical computing. So around the 4.7 million of this are in the optical self-attention part. Okay, as the bottom right is an example generation. You can see the model produces coherent continuation of natural topics like weather, geography. That's they're still weaker on the more technical and science-heavy content. We are actively testing the larger model, including larger parameters, using our photonic chips present here. Okay, so what we can design is actually, before we answer that, it helps to highlight three key frictions that show up when we try to run transformer on the conventional photonic chips. First is the sign conflict. In many incoherent photonic systems, optical intensity is inherently non-negative. A common workaround is to split positive and negative paths and do multiplexings, often lead to more devices per processing times, with a significant efficiency loss. As I mentioned, one of the key problems at the current time for photonics is try to minimize the chip size while maintaining largest computation power, largest matrix size. Second is the mapping bottleneck. I mean that we can use the coherent optical neural network. Mapping a new matrix to the hardware requires complex mathematics, such as singular value decompositions. Doing this for every single token created a massive digital bottleneck. Okay, so this work solves these two issues. It supports dynamic full-range matrix multiplications without sign splitting per pre-processing. At the same time, the photonic integrated circuit layout is compact and routing friendly. There is still a third friction, a physical lag. Even with the mapping overhead is removed, thermo-optical phase shifter are fundamentally slow, with update times on the millisecond scale. But transformer inference demands much faster reconfiguration. To fully unlock dynamic operation of multi-operand MZI, we need high-speed modulator, actually, which we will demonstrate it in the coming slides and also the coming months. We're still taking the full data. For example, like a Kerr effect-based device to provide the required second-order response at much higher bandwidth, but the fabrication and low tuning efficiency is also considerations. Next slide. This is the chip we tape out. As you can tell, the dynamic full-range matrix multiplications. Further helping the speed of the computation, we design and tape out a new chip at AIM to address the challenge. So we propose a new photonic tensor core tailored for transformer acceleration. In this specific case, we have high-speed modulators here. So it introduce three key parameters here: high-speed general matrix multiplications, full-range operand support, and also efficient dynamic encoding with minimum hardware overhead. So in our scheme, the two input vector Vx and Vy are encoded into distinct wavelengths, and we apply a 90-degree phase shift to one of them, and the two WDM streams are then combined with a 50 by 50 directional coupler or MMI, where the orthogonal optical fields interference to produce the X plus minus Y. Balanced photodetectors measured the two output and subtract them, canceling the quadratic terms. as we mentioned in the previous slide. So direct yielding dot product results. Okay, so in other words, this is a fundamental transformer operations. To scale from a single dot product to large matrix vector matrix multiplications, we tile these units into a crossbar architecture to exploit data sharing along the bus waveguides. So this chip has been tapped out and packaged as shown. You can see the electrical packaging and also the fiber packaging. As you know, we use a fiber array, so all the device input and output from one end to minimize the complication of the co-packaging with optics. So next slide showing you the tackle of data sets. We tap out the Photonic Tensor core chip with the integrated of a 2x2 dot product array and high-speed carrier depletion MZI. So this MZI run in a push-pull mode, so we can encode both the magnitude and the phase of each operand dynamically. To validate the core operation, we first calibrate each MZI by sweeping a random inputs and fitting its transmission response. Then we test a single dot products unit for full range element-wise multiplications. So on the left plot, you can see the measured xi dot yi closely following the ideal reference over the entire sign range. To move beyond a toy test, we run a small image processing demo, brand CT MRI fusion. The CT emphasizes bone and calcifications, but MRI highlights soft tissue and lesions. So fusing this is an example of complementary information. We implement the head mount product between the image and a dynamic mask directly on the photonic tensor cord, and then reshape the output back into an image. So the fused result match the digital reference well, and the output form at the bottom show a very low error, as you can show in this chart. So this is as I mentioned, we are using the high-speed MZI to do the modulation. Again, this is showing you the eye diagram of the high speed. At this point, we have 12 gigahertz. We are still in the process of getting higher data also. So to fully unlock the high-speed capabilities of our carrier depletion MZI modulators, again, this is a fabricated AIM. We removed beyond the low-speed testing to high-speed eye diagram. So as you can tell this. So in our sample, we generate the non-return to zero signal with a BERT in our lab. Deliver them with a RF probes and capture the response using a digital communication analyzer to monitor the signal. So the results are shown here. We achieve clear eyes at up to 12 gigahertz from 4 to 8. Again, this is an array, not just a single device. So the probing of high speed is kind of challenging because you need to GSG probe. The device maintained consistent performance stability with a low jitter and robust signal integrity, validating the photonic tensor core chip's capability for high-speed coherent computation. So next slide, we saw after the test, we run several experiments with different data sets. Start from the basic image recognition task. So we evaluate the two benchmarks, Fusion MNIST and also the European satellite data set, Eurosat. The model is the lightweight concurrent neural network where the core convolution and the linear layer are implemented with our chip. As you know, in this case, the linear layer It's mainly for the dot products multiplication to maintain the signal integrity. So everything else like normalization, activation, pooling stay in the standard digital pipeline. So the network size is about 151 kiloparameters for the fashion nest and 621 for Euroset. So we make this realistic for hardware. We use hardware-aware training, including quantization and noise injection. So the model learned to tolerate a limited control precision and device noise. Here we use the sign 5-bit control of the operands encoding. I mean weight and the input together. Okay. So in terms of accuracy, we get about 92.2% for the fashion MNIST and 93.9% for the Euroset. Okay. Again, in this slide, we push the same hardware idea beyond the vision into a language model. Again, we train in the auto-regressive transformer on the Wikitext2 and Wikitext 103 for the next token prediction task. The key differences is that we map the self-attention computation onto our optical engine. So a query, key, and the value matrix are still produced by digital layer. Again, we are using a high-speed modulator, so the computation can be much faster. But the heavy matrix multiplication inside tension are handled by the optical block, and as shown here. Okay, so the language model has about 94.1 million parameters in total, and around 26.6 million those are in the optical self-attention part. So as the bottom right of the example generated, you can see the model produces a coherent continuation. Next slide, we are showing the scalability challenge of the photonic computing. As you know, this is one of the key problems, or is a key challenges when try to replace the electronic computation with the photonic computation. So we move our future plan here. As we discussed earlier, our previous work was primarily focused on the architecture and device level efficiency. However, as we push towards the larger scale optical neural network, even with the specialized designs, footprint and photonic devices remain larger than that of the electronic implementations. I visited Rome Lab a couple of years ago, and they showed me the electronic neural network that can do the very large matrix, much larger than photonics. So right now, what we try to overcome is try to minimize the device size while maximize the computation power per unit area using the photonic chips, so it can really be useful for some Air Force related or DoD related tasks. So in this case, we with the specialized design of the footprint of the photonic devices remain large, as I mentioned already. We try to make in the inverse design here. In other words, traditional forward design photonic computing is built for cascaded modulators, couplers, and MZI blocks. Okay. And the large matrix operation require dense interferometric meshes, which occupy a lot of areas. So the device footprint are at the hundreds of micron to millimeter scale, and the integration density is very small. So to break the size issues here, we explore the inverse designs of photonic computing primitives, where we directly synthesize a target transformation in a single compact device. The free-form nanophotonic structures enable engineered wave interference and bring orders of magnitude footprint reduction with broadband operation. As you know, our department at UT Austin has invited a senior VP from NVIDIA, also senior VP from TSMC, to give talk in very recently. they both mentioned the importance of optical interconnects using photonics. As you know, photonics has takeoff already. As you know, over 4 years ago, I get hired in UT to start the optical interconnects program. So optical interconnects take off, but one thing they have in doubt is really the optical computing because of the density issues. So I think the inverse design we mentioned here is one very pivotal way to shrink the device size while enlarge the matrix multiplications with minimum power consumption. As you know, when you have passive design, putting the modulation or the skin into the design phase, then you don't need to do any energy consumption when you do the computation. So that's the idea, not only to save the area, but also to save the power. So in this framework, manufacturability is co-optimized together with the optical performance, which makes the resulting devices practical to fabrication, and also to pave the way to the scalable optical neural network. As you can tell in the left bottom panel, we have a very small 4 channel WDM. As you can tell, it's only 6 micron by 6 micron. It's which is at least one of magnitude smaller than the existing, of course, WDM devices. So we have more device structures we simulated. We try to do the fabrication in the future. So the photonic inverse design also has its engineering barrier. Scientifically speaking, it can reduce. However, there are 4 key challenges here we try to solve in the basic research context. First, optimize the structure was extremely sensitive to fabrication variations. So small process error can significantly degrade the performance after tap out. Second, the optimization itself is computationally expensive. Since each iteration relies on full wave Maxwell solver over a large parameter space. Third, the loss landscape is highly non-convex and very sensitive to initializations, which means a bad seed can easily trap the optimizer in the poor local minimum. Okay, and the fourth is that design needs to balance the multiple objects such as efficiency, bandwidth, robustness at the same time, which leads to an unbalanced trade-off that are hard to handle by classical optimization. To address this challenge, we propose an AI-assisted inverse design framework with 2 complementary strategies. The first one is surrogate modeling. We use the physics calibrated surrogate model to replace the full wave maximum solver, which dramatically speed up the electromagnetic response evaluation while still providing differentiable sensitivities, so we can keep using efficient gradient-based optimization. Okay, the second one is the generate design. It synthesizes the candidate photonic geometries directly from the optimizers. A much more informed initializations reduces the seeding sensitivity and enable a more effective global exploration of the design space. So those are the tasks we are going to achieve in the coming days. So build on, I'm almost come to an end. Okay, build on this AI-assisted framework, we'll explore 2 specific physical implementation. The first one is the diffractive metasurface structures, where the free-form subwavelength element are arranged to shape the optical wavefront for the target transformations. The second one is the hollow output MMI, where the air hole pattern inside the multi-mode interferometer, as you can see here, is engineered so that the device directly implements the target matrix operations in the single compact footprint. The AI-assisted approach enables multi-objective co-optimization of the optical performance, so manufacturability and also the robustness. And simultaneously, we can discover the compact, non-intuitive optical neural network layout that still can be manufacturable and for the current CMOS foundry. So this is a summary slides. So we present the OM-based multi-operand MZI, and we also have a high-speed dynamically operated Photonic Tensor core, specifically designed to transformer, has been demonstrated. We also have an FPGA-based optical neural network test platform and AI-assisted hardware aware training framework are developed. Okay, and then we have a lot of upcoming tasks working on in the coming years. AI-assisted inverse design of schedule of the scalability and also the energy efficient optical neural network is proposed, and we'll try to develop under the permission of our program manager. Thank you for your attention. Hopefully the concern of NVIDIA and TSMC can be solved, so the optical computing can really becomes a big quantum leap for the future computing. Thank you.